I am going to finish my series on randomization tests by providing a general framework for the one-sample randomization tests. When you watched the videos in this series, it probably occurred to you that you're doing the same thing over and over again, and indeed you are, which is what allows us to establish a general framework. The general procedure is this. Let's define our test statistic to be a linear combination of weighted replacement scores. That is, T is equal to the weight of the first score times the replacement score, plus the weight of the second score times the replacement score, and so on, up to the weight of the nth score times the replacement score. Let's let the weight be 0 whenever the original score is less than 0, and 1 whenever the original score is greater than 0. So what that means is that T, our test statistic, will be a sum of replacement scores, but only of those scores in which the original score was positive. We call R sub I the replacement score for the original score, X sub I. Then all the randomization tests that we have looked at are defined by R sub I, the replacement score. If we replace the score with 1, we get the sign test. Remember that when you're multiplying by 0 or 1, a score of 1 will become 0 or 1. So the sign test is based upon that dichotomous variable, 0 or 1. If we replace the score with the original score, that is, leave the original score intact, then we're performing Fisher's randomization test. If we replace the score with ranks, we're doing the Wilcoxon test. And if we replace the score with z-scores, that is, scores from a standard normal distribution, we're doing the normal scores test. And for each of these tests, we order the difference scores based upon the absolute value of the difference before we make the replacement. The conditions for valid inference are these. The common conditions to all of the tests are that the scores are independent of each other. If we are using difference scores, this means that each matched pair is independent of the other matched pairs in the study. The underlying distribution is conceived of as continuous. When we are conducting a test of the median of differences, the scale of the measurement of that underlying continuous distribution is at least interval, and the distribution of difference scores is symmetrical. I note that this last one is not needed for the sign test, and it is inherent when we use randomization. That is, we don't need to worry about symmetry, we will have it. And finally, if we want to use ordered replacement scores, that is, we are considering every test except the sign test, we can do a test of the stochastic increase of the distribution. Just considering the scale of measurement at least interval, we no longer need symmetry. As you have seen, randomization tests are flexible. They require fewer conditions for valid inference than their parametric counterparts. They maintain the type 1 error rate and allow us to calculate exact p-values. And many times, as you will see in an upcoming video series, they are more powerful than their parametric counterparts.